All right, so large language models, right?
Yeah,
They can do some pretty incredible things.
yeah, they really can. It's pretty amazing.
You give them a few examples in the prompt,
Uh-huh.
and they kind of just like get it.
Right.
Like they pick up on whatever task you're trying to get them to do,
Yeah.
and they're able to generate new stuff, relevant stuff.
And it's all in context. They
Yeah,
haven't been specifically fine-tuned for that particular task.
it's wild, right?
It's incredible. It really makes you wonder how they're doing it.
It feels like magic. Like, where's the learning happening? How can they just adapt like that?
Well, and that's exactly the mystery that's got a lot of researchers buzzing right now.
Yeah, and that's exactly what we're diving into today.
That's right. This ability to learn from just a few examples, in the prompt without having to change their underlying weights. It's really remarkable.
We've got a bunch of sources you shared with me, and we're going to try to really dig into the core findings here.
Yeah,
I'm particularly interested in the mathematical reasoning. Like, how can we explain what's going on under the hood?
absolutely. We'll get into the nitty-gritty of the math.
One of the papers that really caught my eye makes this fascinating connection between a really, really simple type of transformer and a fundamental machine learning algorithm gradient descent.
Exactly. The paper that we'll be focusing on today is called One Step of Gradient Descent is Provably the Optimal In-Context Learner with One Layer of Linear Self-Attention.
Okay, wow, that's a mouthful.
It is.
Who are the authors?
It's by Arvind Mahankali, Tatsunori Hashimoto, and Tengyu from Stanford University.
All right, Stanford. So we know they're doing some serious work there.
Definitely.
And this research is exciting because it actually gives us some solid theoretical grounding for things that people have been seeing empirically.
It's providing a foundation for what we've been observing.
So before we get too deep into the weeds here, let's take a step back to something more familiar. You mentioned linear regression earlier.
Right.
Why is that important in this context?
Well, linear regression is a fundamental concept in statistics and machine learning. It's all about finding a linear relationship between a dependent variable and one or more independent variables. It's a very well understood problem, and that makes it a good starting point for analyzing more complex phenomena.
So it's like a simplified setting where we can really understand what's happening.
Exactly. You can think about it as a basic building block for understanding more intricate things like in-context learning.
So researchers started playing around with these super simple transformers, like the simplest you can imagine. We're talking one layer
Just one.
with linear self-attention.
And no MLP layers.
None of those fancy nonlinear layers that we usually see in Transformer.
They stripped it down to the bare bones.
And they trained these simple transformers on synthetic linear regression tasks. What did they find?
Well, there was this surprising discovery, and this was actually highlighted in earlier empirical work by von Oswald and his colleagues back in 2022. They found that these very basic transformers, they seem to be implementing implicitly one step of the gradient descent algorithm.
Whoa, hold on a sec. They were doing gradient descent,
Yeah, can you believe it?
but they weren't programmed to do that.
No, not explicitly.
It's like they figured it out on their own.
That's right. Imagine you're training this bare bones model on these linear regression problems, and it starts acting as if it's taking this single step in the direction of finding the best fit line for this new data you've given it in the prompt.
That is so wild. It's like without even being told, the model learned a fundamental way to learn. It's almost like, evolution in a way. If you've got this super simple learning mechanism and you expose it to the right kind of data, it naturally stumbles upon the most efficient way to learn just step-by-step improvement, just like gradient descent.
It's a really profound connection.
Totally. And this paper that we're talking about by Mahankali and his team, they took this empirical observation and they actually went a step further, right?
They did. They provided a mathematical proof for it.
Okay, so they showed mathematically that this is really what's happening.
Well, they proved it for a specific case, but yes.
And what's that case?
So their theoretical breakthrough shows that if you have input features, let's call them $, that are drawn from a standard Gaussian distribution, and you're like a perfectly symmetrical bell curve, then the one-layer transformer that minimizes the pre-training loss, it will actually implement one step of gradient descent on at least squares linear regression objective.
Okay, so let me try to unpack that a little. Standard Gaussian distribution. That means that the data points are spread out evenly in all directions, right?
That's a good way to visualize it.
It's like a perfectly round cloud of data points.
Exactly. Mathematically, it means the covariance matrix is just a scalar multiple of the identity matrix.
Right, right. And the paper goes on to describe the pre-training data setup in detail, right?
Absolutely. They explain how the data is generated. So the input features together, they come from this normal distribution with mean zero and a covariance matrix. That's the identity matrix.
And what about the output, the high dollar?
For each sequence, they also sample a weight vector, let's call it $50, from the same distribution.
Okay.
And then the output, $, is generated using a linear equation. It's basically the dot product of the weight vector and the input feature vector plus some random Gaussian noise.
So you've got your input features, $20, your weight vector, $20, and then the output is just a linear combination of those, plus a bit of randomness.
That's it.
And this random noise is important, right? It simulates the kind of messiness we see in real world data.
Exactly. It captures the fact that in the real world, things aren't perfectly linear.
So the model sees all these examples of a vid and Yale dollars in the prompt,
Yeah.
and then it's asked to predict the output for a new input, right? Which they call X1 dollar.
Uh-huh. And what's really fascinating is that the paper proves that the optimal transformer learns to make this prediction using a very specific equation.
Okay, hit me with that equation. What does it look like?
It's eta 7 top.
All right, let's break that down.
Sure. So Hat's dollar is the predicted output for the new input, X1 dollar. And you see that it's basically a weighted sum of the training outputs.
Weighted sum, okay.
And the weights are determined by the outer product of the training inputs, Axial and the new input, X1 dollar. And then the whole thing is scaled by this factor, eta dollar.
And what's the zeta?
That's a really important part. It essentially acts as a learning rate. It controls how much the training examples influence the prediction for the new input.
Ah, so it determines the step size, like how quickly the model adjusts its prediction based on the examples it's seen.
Exactly. And the paper derives a specific formula for this optimal learning rate, eta dollar.
Okay, so the transformer, just by training on this specific kind of data, learns to take a step in the right direction using gradient descent. Now, this is where things get even more interesting. What if the data doesn't come from this nice, clean, perfectly symmetrical distribution?
Right. What happens when the real world throws us a curveball?
Yeah, what if the data is messy? What if it has some kind of structure or bias to it?
That's a great question, and the paper explores exactly that. They look at what happens when the input features come from a non-isotropic Gaussian distribution.
Non-isotopic, meaning that the data isn't spread out evenly in all directions.
That's right. The data might be more spread out in some directions than others.
So like an oval-shaped cloud of data points instead of a perfectly round one.
Exactly. And they also adjust the distribution of the weight vector to account for this different covariance structure.
Okay, and what happens to the learning algorithm in this case?
This is where it gets really cool. The algorithm transforms into something called preconditioned gradient descent.
Preconditioned gradient descent. That's a more sophisticated way to optimize, right? It takes into account the shape of the data.
You got it. It's like having a map of the terrain and knowing which directions are steeper than others. You can take bigger steps in directions where the terrain is relatively flat and smaller steps where it's very steep.
So the algorithm adapts to the geometry of the data.
Exactly. And the equation for the prediction in this case also changes. It becomes hat top x plus $1. You'll notice that the inverse of the covariance matrix, sigma, is now being applied to the input features.
So the shape of the data encoded in the covariance matrix is directly influencing how the algorithm learns.
That's a key takeaway. The distribution of the data isn't just some side detail, it's actually shaping the learning process itself.
This is blowing my mind. So we've talked about the shape of the input data. What about the output distribution? The paper mentions something about nonlinear targets.
Right. They explore what happens when the relationship between $I and $Y isn't a simple straight line. It could be a curve or some more complex function.
So instead of just a simple linear equation, you have a more complicated function connecting the input and output.
Right. They define the output as $Y epsilon plus epsilon dollar, where $5 is this potentially nonlinear function.
And they still train this simple linear transformer on this data.
They do, and that's where another surprising result comes in.
What happens? Does the transformer try to learn this complex nonlinear function?
You might expect that, but that's not what happens.
Really?
The paper proves, and this is maybe the most surprising finding of all, that even when the true relationship between the input and output is nonlinear, the one-layer linear transformer still learns one step of gradient descent on a least squares linear regression objective.
Hold on. So even with all this complexity in the data, the transformer is still stuck in linear land.
In a way, yes. The prediction equation stays the same. But of course, the value of the learning rate, $8, might change depending on the specific nonlinear function involved.
So even though the transformer has the potential to learn something more complex, it's limited by its linear architecture. It can't really capture the nonlinearity in the data.
Exactly. The author suggests that this simple linear architecture acts as a bottleneck. It doesn't have the flexibility to really grasp the nonlinear relationships in the data.
So it's like trying to fit a square peg in a round hole. The transformer can only do so much with its limited tools. Now, I know the paper delves into the mathematical reasoning behind all of this.
It does. It's pretty heavy stuff.
And while we won't go through all the proofs here, can you highlight some of the key mathematical insights for us?
One of the central pieces of the puzzle is something called Lemma 1 in the paper. This lemma connects the pre-training loss of the transformer to how well it can approximate the best possible linear model, given the data.
So essentially, it's saying that the transformer is being pushed to be as good as a linear model can be, even when the true relationship is more complex.
That's a good way to put it. And another key insight is how they exploit the properties of the Gaussian distribution. They use its rotational invariance and symmetry to simplify the calculations.
Gaussian distributions are so well behaved mathematically.
They really are, and these properties allow them to make some clever simplifications and really get to the heart of what's happening.
So it's this beautiful interplay between the structure of the model, the characteristics of the data, and the mathematics of minimizing the loss function that leads to these results.
Absolutely. And the final aha moment is the realization that under these specific conditions, the transformer is mathematically compelled to implement gradient descent. It's not just a coincidence, it's a direct consequence of the optimization problem and the model's limitations.
Amazing. And the paper mentions that other researchers were working on similar ideas at the same time?
Yes, they acknowledge the concurrent work by An and his colleagues, as well as Zhang and his team.
And what did those other researchers find?
Well, they had very similar findings. They also showed that simple transformers with linear self-attention tend to learn one step of gradient descent.
Okay, so it seems like multiple groups were converging on this same insight.
Yeah, and some of these other papers even extended the analysis to multi-layer transformers.
Ooh, that's even more complex. So we're starting to see a more general picture emerging here.
We are, and it's really exciting.
So we've covered a lot of ground here, diving into the theoretical foundations of all this. Can you sum up the key takeaways for our listeners?
The biggest takeaway is that even a simple transformer with just one layer of linear self-attention can learn to perform a fundamental optimization algorithm like gradient descent.
And it does this just by being exposed to data without any explicit programming.
Exactly, and the type of algorithm it learns is directly tied to the distribution of the data it sees.
So the data itself is shaping the learning process in a profound way.
Absolutely, and we also saw that even when the true relationship in the data is nonlinear, this simple transformer still clings to linear regression and gradient descent. It's limited by its architecture.
It's fascinating how the model's limitations actually tell us something about how it learns.
And this brings us back to our initial question about the almost magical in-context learning abilities of large language models.
Right. How does all of this relate to those massive, complex models that seem to learn so much from just a few examples?
Well, even though this one-layer linear transformer is super simplified compared to the real behemoths out there, it gives us a valuable theoretical starting point. It hints at how fundamental computational primitives like gradient descent can emerge implicitly during training.
So by understanding how these simple models learn, we can start to build up an understanding of what might be happening in those much larger, more intricate models.
Exactly. It's like looking at the building blocks of a skyscraper. By understanding the individual pieces, we can begin to appreciate the complexity of the whole structure.
That's a great analogy. And so for our listeners out there, consider this. If the distribution of the training data so strongly influences what a simple model learns, what kind of algorithms are emerging within those massive language models that have been trained on all the messy, complex data of the internet?
What kind of optimization landscapes are they navigating? What kind of implicit knowledge are they acquiring just by being exposed to that vast sea of information?
It really makes you think about the deep connections between data, model architecture, and the emergent intelligence of these systems.
It certainly does. And for those who are interested in exploring the mathematical details further, we highly encourage you to check out the papers we've mentioned, the work by Mahankali and his team, as well as the papers by An et al. And Zhang et al. Offer a rigorous and fascinating look at the theoretical underpinnings of in-context learning. And thinking about how these principles extend to more complex architectures and different learning paradigms is a really exciting frontier in machine learning research.
Absolutely. There's so much more to explore and discover in this space.
Definitely. And it's only going to get more interesting from here.
Thanks for diving into this with me.
It was my pleasure.
Until next time.
See you then.